On January 15, 2022, a volcano in Tonga exploded so violently that satellites saw a white cloud spread across the Pacific in minutes. A tsunami followed, but far from Tonga. Some of the first wave signals reached instruments earlier than a normal ocean-only model said they should. How can a tsunami arrive too early? The first answer is already visible in this image. The blast did not move only water. It also launched a pressure wave through the sky. That pressure wave raced outward at about 312 meters each second, close to the speed of sound. Below it, ordinary tsunami waves crossed the deep ocean more slowly. So this was not one simple ring leaving one point. It was two linked races, a water wave moving away from Tonga, and an air wave pushing on the ocean as it ran. Most tsunamis begin with an earthquake. A block of seafloor jumps, lifts a huge column of water, and sends long waves outward. In deep water those waves may be fast, but their speed depends on depth. The deeper the water, the faster they move. A warning center can use the source, the ocean depth, and the travel path to estimate an arrival time. Hunga Tonga Hunga Ha'apai was different. It was a shallow submarine volcano, about 60 kilometers north of Tonga's main island. The eruption tore apart most of a young island that satellites had watched grow since 2015. Near Tonga, surveys found run up as high as about 20 meters, 65 feet in places. A source near the volcano clearly displaced enormous amounts of water. But what moved that water? Scientists tested several answers. The explosion itself, collapse of the caldera, rock and ash falling into the sea, hot flows racing over the ocean, and the pressure wave in the atmosphere. More than one mechanism could act at the same time. That matters, because each one leaves a different pattern and a different clock. Start with the part that behaves like a classic tsunami. A sudden push near the volcano creates a long wave. In 4-kilometer deep water, a simple long wave estimate gives a speed near 710 kilometers per hour. That is jetliner fast, but still slower than the pressure pulse moving through the air above it. The explosion squeezed the atmosphere into a low-frequency pressure pulse called a LAM wave. Barometers recorded it around the world. NOAA measured its travel near 312 meters per second, or about 1,123 kilometers per hour. It circled Earth more than once. Yet the strange part was not simply that air moved faster than water. As the LAM wave crossed the ocean, its pressure pressed down and released the sea surface. Imagine running a finger across a drum while the skin can move beneath it. The push was small far from Tonga, but it acted along an enormous moving line. That moving pressure created a tsunami, a tsunami driven by weather-like pressure, not only by motion at the seafloor. This air-driven ocean signal traveled with the atmospheric wave, just below the speed of sound. In a global study, parts of the observed tsunami reached distant coasts about 1.5 to 2.5 times faster than a standard point-source tsunami would. Japan saw signals in under 7 hours. Chile saw them in under 10. NOAA's DART boys made the puzzle harder before they helped solve it. A DART station has a pressure recorder on the seafloor. It detects the weight of water above, but the Tonga pressure wave also changed air pressure at the surface. The instruments recorded a mixture, the fast air-linked signal first, then the slower water wave train. Researchers had to separate those arrivals. NOAA built one model from the later DART data, excluding the first pulse linked to the atmosphere. Then it built another model in which a moving LAM wave forced the ocean surface. The second model explained the early arrival at most distant DART stations. Neither model alone explained every height near Australia and New Zealand. That mismatch is evidence, not failure. Close to Tonga, explosion, collapse, debris, and hot volcanic flows could build short, powerful waves. Far away, the atmospheric wave could create an earlier, lower signal across several ocean basins. What a coast received depended on direction, ocean depth, islands, bays, and the way several wave trains overlapped. The result was global. Instruments detected the tsunami across the Pacific, Atlantic, and Indian Oceans, and even in the Caribbean and Mediterranean. Some waves appeared in places where Tonga was partly blocked by land. A normal water wave cannot cross a continent. The pressure wave could cross above it, then make new water motion on the far side. The first arrival was not always the largest. The fast atmospheric signal could announce the event, while slower ocean waves and reflections arrived later. In ports and bays, the shape of the coast could amplify certain periods. That is why a weak first surge never proves the danger is over. Return to the satellite image. The giant white ring was more than a dramatic cloud. It was visual proof that the eruption coupled the ocean, atmosphere, and even the upper edge of space. The plume reached about 58 kilometers high. The pressure disturbance kept crossing the globe for days. Tonga had turned the whole planet into part of the measuring instrument. Earthquake tsunamis give warning centers a familiar starting point. Locate the quake, estimate seafloor motion, and model the water. A volcanic explosion may give no single clean source. It can make local waves before every mechanism is known, while an atmospheric pulse creates distant signals on another timetable. Forecasting must combine pressure sensors, sea level gauges, satellites, and several models. The practical rule remains simple. If officials issue a tsunami warning, move as directed and stay away until the all clear. Near a volcano or after strong shaking, natural signs such as sudden sea retreat, a rapid rise, or a loud ocean roar mean move to high ground without waiting. Do not return after the first wave. Tonga showed why the clock can have more than one hand. The Tonga tsunami did not break physics. It exposed a second path. One part began as displaced water and crossed the ocean at the speed set by depth. Another began as pressure in the sky, ran near the speed of sound, and kept pushing the ocean beneath it. The wave arrived too early only because the old question assumed there was just one race.